Let's be honest, we're living in a world that is just overflowing with information. It's coming at us from all directions. So the big question is, how do we find the actual meaningful signal inside all of that noise? Today, we're going to dive into the really cool tools that help us do exactly that, make sense of messy data.
I mean, just think about it. Every single second of every single day, our world is generating an unbelievable amount of data. We're talking about everything from what you're posting on social media to massive scientific experiments. It's all pouring in, creating this vast, endless digital ocean.
You know, having all this data is one thing, but actually understanding it, that's the real puzzle, isn't it? It's so easy to get lost in the numbers, to get overwhelmed by it all. So how in the world do we separate the important patterns from all the random, meaningless static?
Yeah, because simply collecting data, hoarding it, doesn't get you anywhere. The real mission, the whole point, is to turn that raw, chaotic information into something you can actually use, into actionable intelligence. Without the right approach, like the side says, we're literally just drowning in it. So where do we even begin? Well, the most basic, fundamental way we start to make sense of things is by looking for simple connections. We start small, by just looking at two things at a time. And this first step, it actually has a name, bivariate analysis. You should think of it like a data detective's first move at a crime scene. It's all about picking up two clues, two variables, and asking a really simple question. Hey, are you two related somehow?
And you know, the way we investigate depends entirely on the kinds of clues we have. So, for instance, if we're comparing two numbers like a person's height and their weight, we're basically asking, do taller people tend to weigh more? Simple enough, but if we're looking at categories, say gender and product preference, the question changes. Now we're asking, do different groups like different things? It's all about asking the right question for the kind of data you're looking at.
Now, these relationships, they usually go one of two ways. You can have a positive trend, which is when one thing goes up, the other thing tends to go up too. The classic example is study hours and test scores. The more you study, the better your score. Or you can have a negative trend. That's the opposite, right? As one thing goes up, the other goes down, like maybe more time spent watching TV correlating with lower grades.
And we can actually put a number on this relationship to see how strong it is. In one study, looking at hours studied versus marks scored, the correlation number was 0.926. Now, a value that close to 1, that's not just a hint. It's practically a giant flashing neon sign telling you there's a really, really strong positive connection there. A very clear signal indeed.
Okay, so looking at two things at once is great. It's a solid start. But what happens when our nice, simple little world explodes into a data set with hundreds, maybe even thousands of variables? Suddenly, comparing them two by two just isn't going to cut it. To wrestle with that kind of complexity, we need a much more powerful tool. We need something that can look at the whole chaotic mess and somehow find the main story hidden inside.
And that tool is called Principal Component Analysis, or PCA for short. Honestly, you can think of it as a kind of data superpower. Its entire job is to simplify a massive data set by boiling it down to just its most essential ingredients, its principal components, without losing the stuff that really matters.
The way it works is actually pretty methodical. As you can see here, PCA follows a series of steps to systematically find the most important patterns. It starts by making sure all the variables are on the same scale. So something measured in millions doesn't completely overshadow something measured in single digits. And it finishes by creating a whole new, much simpler map of the data.
This table really gets at the why behind each of those stages. Standardization, like I said, is all about fairness, making sure no variable gets an unfair advantage just because its numbers are bigger. And then there's this eigenanalysis part. That's the secret sauce. It's the mathematical engine that figures out the new directions in our data that capture the most interesting information.
But, and this is a huge but, this superpower comes with a pretty big trade-off. We gain incredible simplicity, but as this quote points out, we lose the original, easy-to-understand meaning. It's like getting a perfect one-page summary of a huge novel. You totally get the plot, but you lose all the beautiful language and character details. These new components are just mathematical recipes, not something simple and intuitive like age or income. So here's the deal in a nutshell. On the one hand, PCA is absolutely amazing for cleaning up noisy data, for making machine learning algorithms run faster, and for just focusing on the big picture. But on the other hand, you lose that direct meaning, and you do risk accidentally throwing away some smaller, more subtle patterns that might have been important. It's a balancing act.
Okay,
So we've used PCA to tame our complex data, to cut right through the noise. So, now what? What can we do with this new, cleaner, simpler dataset? Well, this is where it gets really fun. This is where the discovery happens.
Right. With our simplified data in hand, we can now use another awesome technique called clustering. This is how we find the hidden structures, the natural groupings just sitting there in the data. Think of it like someone handing you a giant mixed-up bag of marbles, and you finally get to sort them into neat piles based on their color, their size, and their pattern.
And of course, there's more than one way to do it. You've got methods like k-means, which is perfect when you already have a hunch about how many groups you're looking for. It's kind of like telling a librarian, sort all these books into exactly 5 genres. Then you have something like hierarchical clustering, which builds this beautiful tree of connections. That's more like letting the librarian create a detailed family tree showing how every single book is related to every other one.
But a huge question is always, how many groups should I even make? Well, there's a popular trick called the elbow method that helps you decide. You basically look for the bend in the chart, that exact point where creating more and more groups stops giving you much more useful information. It's all about finding that perfect sweet spot between being too simple and being way too complicated.
All right, so we've gone on this whole journey, from messy data to simple pairs to powerful simplification, and finally to discovering hidden groups. But why does any of this techie stuff actually matter out here in the real world? Well, the impact is absolutely massive, and it is everywhere. I mean, these techniques are the secret engine running behind so much of the technology we use every day. They help machine learning models figure out what's important, they let engineers spot bugs in super complex software, and they help companies understand how you are actually using their products.
And that really brings us right back to the main idea, doesn't it? This whole process, from a simple two-way comparison to a complex clustering analysis, it all has one fundamental goal: to take a meaningless flood of raw information and transform it into real, usable knowledge that can help us make better decisions.
And that leaves us with a pretty fascinating thought to end on. We are generating more data right now than at any other point in human history. With tools like these getting smarter and more powerful every single day, the real question is, what incredible, maybe even world-changing patterns are we just about to uncover next?